everyone. Welcome and welcome back. This is our 5th session at Hackaday on quantum computing. And I know there are newcomers every week, so just to show people there are a lot of resources. You can find most of the links through the Hackaday project is the introduction to quantum computing. So every Wednesday and Sunday, I post some comics. You can read about the topic. The topic is usually what we talk about during this class on Sunday. So if you look at it on social media or Hackaday, you figure out what topic we'll talk about. So every Sunday we meet for 30 minutes describing one concept. And we would also use some of the Microsoft official resources for practices and references. So I know there are newcomers, and we have 4 recordings so far from the past class. So if there's anything from today's class that's not clear to you, feel free to ask question and also go back to the previous recordings. So just now I heard there might be some problems for people not being able to view previous recordings. If that happens to you, feel free to let me know, and I'm trying to check if I can view those videos also. So just to recap, from last Sunday, we discussed the concept of gates, and we introduced a graphical presentation called the block sphere to show that any qubit is representable on these sphere that is telling us what the state vector is. So anywhere on this sphere, we can describe it with angle theta and phi. The angle would then tell us the amplitude of each state, how much of 0 is in there and how much of 1 is there. And 0 and 1 are 2 states in superposition, and they are in these special locations on the poles. And because we can describe, if anyone's not muted, please do so right now. And after the 30 minutes, we'll do the question and discussion, and you can unmute yourself then. Thanks. The block sphere, because it shows us the angles, that in order to manipulate the state, is basically manipulating the point on the sphere. You can use a matrix, a 2x2 matrix. One of them can change the angle phi, phase phi. The other is changing the angle theta. And you can apply to this vector that's describing the qubit. That's what we talked about last time. So we introduced a few, is the slides not full screen? I see full screen here. Sorry. Maybe you can expand it a bit. Sorry about that. So last time we also introduced some commonly used gates. The Hadamard H gate, remember that's applying to either, it can apply to any vector, but if you apply it to 0 or 1, you can see that they change the location to this middle point. We call them plus state and minus state. This is a single qubit gate. And we also introduced those X, Y, Z Pauli gates that are also single qubit gates. They can rotate your state around these X, Y, and Z axes. And we mentioned that single qubit states can be represented on block sphere, and then you can use these 2x2 matrices to manipulate them. But of course, there are more qubits that we need to worry about, and the block sphere would no longer be used when we expand to multiple qubits. And also there are gates that are used to apply to multiple qubits. Now, the one of the most popular, mostly used multiple 2-qubit gates is the CNOT. This is a 4x4 matrix.
Hello.
And I think there might be something similar in
Now joining.
Okay. I think there's something similar in classical computing. There's something like a controlled NOT gate. So it's the same idea that is basically allowing your first qubit to be a control qubit and your second qubit to be a target. And what it does is basically say if the control qubit is 0, then the target qubit doesn't change. If the control qubit is 1, then the target qubit has to flip. We can see this from this 4x4 matrix. The form of this is almost an identity matrix, which doesn't change anything. However, the last quadrant is flipping the location of 0 and 1. And what it does is really switching your vector. These 1x1 here is 2x2 with the 2 ones here in the first quadrant is telling us is preserving the first qubit, but then when you apply it to the second qubit, it depends on your first qubit what to do with it. The effect of CNOT is that if your first qubit is 0, then your second qubit doesn't change. If your first qubit is 1, your second qubit will be different. I would ask people to try the math, to try applying this 4x4 qubit to your vector. And this CNOT is very important that almost, well, all of the algorithms that are useful that we're gonna look at would use it. And there's something that I mentioned earlier that also does that, is some manipulation, some property for quantum mechanics that is being used in every algorithm. And I would introduce you later. So this is just to show you the matrices here. For the interest of time, I would not force you to do this matrix, but if you don't remember, this is how you do matrix multiplications. And please do try this at home. So we don't use block sphere anymore as a graphical representation. I already explained last time that it won't be very helpful because block sphere can only represent in a 3-dimensional space for a vector. And when you have multiple qubits, that's a multi-dimensional, more than 3-dimension geometry space. So for us, we can't really see anything beyond 3 dimensions. So we're not gonna use block sphere. It's only helpful when you want to see how that 1 qubit can change. But we can introduce another graphical representation that can help us when we have a few more qubits. It's very simple. It's like the music notes where line would represent how your music progress over time. We also use the line to represent the progression with time, but this time is to just use the line to represent a qubit. So the state A here is our qubit, and you can draw a line to represent it. If you have 2 qubits, that's 2 lines, 3 qubits, 3 lines, n qubits, you draw n lines. So in terms of the CNOT gate that we just talked about, it has a symbol that connects the 2 lines. Because it's a 4x4 matrix, it acts on 2 qubits. And it also tells us the top line, the one with the black dot is the control. And the one with this circle cross is target. That's it. This is a circuit representation, very straightforward, and especially for the single gate qubits, you can just write it down like a box with the label, with the letter. And there are a lot of gates out there. You can just do a search online. You see this graph in Wikipedia. This is showing some of the most commonly used gates. And you can see there are other control gates. And there are also these swap gates that basically swaps the two qubits. You can also have this CC knot that is having two controls and one target. So if you're interested, you can try these methods and see how they do, what they do to your qubits. And gate, we also mentioned, is a reversible property. But measurement is not reversible. Yet we can still use a graphic presentation to represent the measurement. It looks like a probe, a dial. So this is how we draw measurement. Is also what's different is that it's not reversible, and after a measurement of a qubit, you get a piece of classical information out. Because you cannot then reverse it back to quantum. So we use two lines to represent the output is classical. That's it. So here is what I mentioned. There's something that we use in all the algorithms is entanglement. We can actually use what you have learned so far to construct entanglement. And namely Bell states when you have two qubits. That's the mostly used property in a quantum algorithm. You always want to entangle your qubits to make your algorithms useful. And to entangle two qubits, all you have to do is to first apply a Hadamard gate and then put a CNOT gate to combine the two states. So let's take a look at how this really works step by step. This table already tells you what your outcome will look like. So if you have these four possibilities, your outputs will be those four Bell states. Bell states, if you haven't learned it, it is introduced in, I think, the third session. So please take a look after class if this is a new term for you. Let's just take a look at the math, how everything works out. So that also can help you and remind you how it works. What happens if you apply a H-gate to a qubit? So say if you had a 0 in your first qubit, you apply a H-gate, then this is the first superposition you will get. Is equally distributed among 0 and 1. Like what I showed earlier in the block sphere, they would move the basis for this top-down 0 and 1 on the z-axis to the middle one along the x-axis. Basically, the Hadamard gate, changes your basis of the system. If your first bit is 1, you get the same thing except the minus sign there. This is our minus state. So, okay, so that's our first step, applying to the first qubit. Then it depends on what your second qubit initially is. So this is how you can write it out. H times your first qubit, you write the outputs there, and then you do your second qubit, you just add it in here. So having the 0 and 1 inside the same bracket or in two separate brackets is the same thing. So you write this out here. then you will need to apply a C0. So given your first qubit is 0, if then your second qubit wouldn't change in this case, so it would be 0, 0 here. But if you are looking at this possibility here, if your first qubit is 1, then your second qubit have to flip, so it becomes 1, 1 here. So now, just you could write out all the matrices to do the full calculation if you want, but just by looking at this, you already can see why the answer is this. So 0, 1 staying there, 1, this one will be 0, so that's 1, 0. Similar here with the minus signs. So now that's how you make a Bell state. Once you put this into a Bell state, then they are entangled 2 qubits. You cannot separate them out until you do a reverse. So remember, all the gates are reversible. You could then disentangle them by applying a C0 and then an H gate. So try it out yourself. Let's put everything together into a full algorithm. This is the teleportation circuit. I mentioned teleportation before without really showing you any of the math and these circuit representation. So let's review the story here. When we have 2 entangled qubits, so say Alice and Bob, they are trying to communicate. They first would prepare a pair of entangled Bell states, and then Alice then obtains a new qubit, A dash, and she wants Bob to know what this is, but she can't directly tell him, just for the sake of argument. She maybe doesn't want other people to see it, or whatever reason, she cannot directly give Bob a dash. But then she could entangle her 2 qubits that she has in her possession. Then she does a measurement to her qubits. Based on her results, she can tell Bob what to do with his qubit, basically applying some gates to change Bob's qubit to a dash. So this is the teleportation circuit. This is how teleportation algorithm works, is that there's no direct exchange of qubits, but then you use entanglement to let the other person know the information, the new information that you want them to know. So it's kind of teleported your information to them without the physical exchange. And because they can do this because they know what the outcome would be based on the initial entangled state that they put their qubits in. So let's look at the circuit again. I just went through the story, but this is how they can do it in the algorithm. They can entangle 2 qubits using the H and C0, and then she can entangle hers using H and C0. And then she just do a measurement of both of her qubits. Based on the result, Bob would either do an X gate or a Z gate, or X plus Z gate, or nothing. So this table shows if Alice's 2 qubits after she does the measurement becomes 0 and 1, then we know Bob's qubit will be this one, and he doesn't have to do anything. If the first 2 qubits are 0 and 1, the third qubit will be this one. Oh, I didn't mention that. Just say using this as Alice's new qubit. I will show you in detail how it works in a bit. So if Bob gets this state, then he has to apply the X gate in order to get to this state. similarly with the other two options. So let's just take a look in detail what this is all about. So let's just, for the sake of argument, this table applies to the Bell state. If they start their entanglement with this Bell state, this is the table that they will get. Step by step, they first prepare their qubits in this plus Bell state. And then we say, just let A dash B this arbitrary state. We don't know what alpha and beta are. Then you have Alice's new state A dash, and part of one of this first qubit belongs to Alice. So the whole system is A dash and phi plus. If you write the whole thing out, this is your phi plus, this is your A dash, and you can expand it. It becomes 4 terms. These are also, you can see this is what you would get just by writing down the qubits one by one. So 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. So you get 4 possible terms in superposition. Now you want to entangle Alice's 2 qubits, which are the first qubit and the second qubit. You do a C0 there, which would then apply to the first 2 qubits and change the setup into this state here. And then you apply a H gate. So I should slow down. There's a lot of zeros and ones. So I'm going to talk slowly. When you apply a H to the state here, is only applying to the first qubit. So you just write out what you would expect from 0 and 1s. So that's what your whole system, the 3 qubits, become after you do this entanglement. Now, this is what your system looks like after this step. So then what happens if you do a measurement? So Alice has these 2 qubits. She would do a measurement for each. If the first qubit is 0, the state after the measurement will only have these 2 terms, because the other 2 terms have 1 as their outcome. So those will cancel out. If her outcome is 0, then it's not possible to have these terms still in your system. So only these 2 terms are left. And this is written in a way that it shows you these 2 qubits first that belong to Alice. Then she does another measurement. If again she gets, so this measurement is now on the second, on her second qubit. If she gets another 0, then this term is then eliminated. It's not possible that she would measure 0 when this term is 1 here. So you only have this term left in your system after these 2 measurements. Now look at this form here. This is where we want Bob to know. This is A dash, this arbitrary state. So without doing anything, Bob's state will know when he does a measurement, he will get this. It automatically comes out as a result that this arbitrary state is the same thing in Bob's hand. So this is a very interesting thing about teleportation. circuit that shows you how entanglement works is that there's no exchange of circuits, but then you know what Bob will get. So this is just saying, using this first example here, but then if you pick another one like 1, 0, if Alice's first qubit is 1, then these two are the terms that the system will be left with after the first measurement. And then if your second qubit is 0, then this will be the term. So what Bob will have will be this bell state here. And Alice looks at her table, knowing that this will be what Bob gets. She calls Bob and tells him, do a Z gate to your state. Then you will get what I want you to have. So that's it. This is our famous teleportation algorithm. There are a lot of other algorithms, and it will get more and more complex. When we have a small number of qubits, we can represent the system nicely with a circuit. However, when we have more complex algorithms that we involve a large number of qubits, we would get into a very messy state where we have to draw all of the qubits and seeing how they change every step. That becomes not scalable. So these are some of the most famous algorithms that really build the foundation of quantum computing. We would go into a few of them in the next classes. We can still write circuit representations for them when we pick a small number of qubits. But then think about the possibility you have to handle 1,000 qubits to really write something useful. Then it's not really scalable. That's when we really need to have a high-level quantum algorithm to represent those, high-level quantum language to represent those algorithms. That's like when you write a classical algorithm nowadays, you don't look at how your individual transistor behaves. So same thing in quantum computing, you wouldn't want to look at how each individual qubit behaves when you do a really complex quantum algorithm. So we would get into Q-sharp, the language that is high level and is full stack, specifically designed for quantum computing. We would try to learn it and use it for constructing circuits and build much bigger programs. Last class, I showed people there are some very nice exercises that we developed to teach people about Q-sharp. This is quantum katas. You can go to this link. The slides will be shared on Hackaday, but you can also just search quantum katas. This will pop up. They have a nice set of very interesting problems building up from very simple to gradually more complex. And we have tutorials to guide you through those. Based on what we have learned so far in the past 5 sessions, including today, these are the ones that you can already take a step at with not much looking for information. Just follow the tutorials. You should be able to do a lot of the basic gates and the superposition and measurements, teleportation, katas. And we have some other algorithms that we haven't talked about in these sessions yet. You can also just take a look at it. It's got a very nice self-paced explanation. Try to do some of these before the next few classes, but we would get into some of these later. And I think because of the interest in this class, I wonder perhaps before we go into those algorithms, we should take a detour and talk about some of the hardware systems. Yeah, I think people will like that. And there might be a Twitch live stream for this class starting next week. I'm still trying to figure out how that works. I haven't done any Twitch streaming before, but Microsoft has this channel that I could use. So maybe once, if that's set up, then I could add a link there. And I don't know how that works, combining a Twitch streaming with the Teams. So we'll figure out the technical things and see what works best. I think Teams works really well, so we may keep this and have Twitch open at the same time. But if it doesn't support two tools, then I may update a Twitch stream on the Hackaday projects. Thanks. Yeah. Thanks, Aaron. Yeah, I would ask you questions if we can't solve it. And then we would also have some sessions on learning Q# and writing some algorithms using the quantum development kit and the katas. Okay, that's it for today. We can stay for a couple more minutes to answer questions. I will take a look at the chat here to see if there's any question I can answer here. Feel free to speak up, unmute yourselves, or message here.
Hello, can you hear me?
Yeah, hi.
Hi, how you doing? I just want to know, I was just wrestling with the Jupyter notebooks over the week, and I keep getting disconnected and having to start over again. It's not a quantum computing question, it's a Jupyter question.
Yeah. It's using Binder, and it has a 10-minute timeout. That's really annoying, I know. You could use the local, you can download Jupyter Notebook. On the quantum computing documentation page, you can find how you can run it locally without connecting to the internet. Or you can download the quantum development kit. Let me share my screen and show you where things are. Yeah, so if you can do the katas without interruption, then you can do it. But if you want have other windows open and doing other things, then it times you out for 10 minutes after 10 minutes. Yeah, let me give you this share screen. So this is the Microsoft Quantum documentation page. You can just do a search to find it. It's pretty easy to find. And there are several different options for you to write Q# code. So there's a quantum development kit extension, and you can use Visual Studio or Visual Studio Code to run that with a driver, a C# driver. And there's also a Python driver, so you can also use this option. The Jupyter notebooks, you can follow these to run it locally on your computer, so you don't have to use Binder. There is also, we constantly update this documentation page, and when we release new features, it will be shown here. There's actually gonna be a driverless option too, so watch out for that very soon. Any
Okay,
other?
so
yeah.
If I do the VS Code option, will I have everything I need for to run the katas except the kata material?
Yes. Yeah. So you can directly search for the katas. You can also find it here from the Learning Resources tab. So Learn Q# with the quantum katas, which then describes it, and then you can follow this link.
And the VS version will also check my
So you can just clone it to your computer. You come, yeah, and you can just run the same code as there.
Okay, thank you.
Yeah, thanks for asking.
Yeah, hey, Kitty. This is
Hey,
Bob.
Bob.
On the first slide today, I
Mhm.
think it was the slide where you went over 2 qubits, and the first one you put into through a Hadamard gate, and then you use it as the control gate in a control knot to entangle it with the second qubit.
Are you talking about the teleportation or
I think it was just before the teleportation.
the Bell state?
Yeah, just that
Yeah.
simple example there.
Uh-huh.
And so in this example, I'm having a little hard time reading the math.
Mm.
Basically, there's an equal chance that when you measure it, that you're going to get any one of the 4 possibilities. Is that true?
No. Depends on what your input is. This will be the output you get. So if you want to create a Bell state that looks like this, then you need to start with 1, 1. So you have to prepare your initial qubit into 1 and 1, and then do this H naught and H and C naught to make it into this.
I'm back.
Yeah.
I got disconnected.
Oh, okay. Sorry. I was saying that you have to prepare your initial states. These are the inputs and the outputs you will get based on what input you have. So if you want to prepare a Bell state, yeah, that looks like this, you have to make your input qubits 1, 1.
Oh, okay. That clarifies it for me. Because my question was going to be that how does that? So if you just applied a Hadamard gate to both qubits, they wouldn't be entangled.
No, because Hadamard is a one single qubit gate. You're just applying them separately. There's no connection between the qubits. The C naught here is connecting your 2 qubits. And this Hadamard here is only applying to the first qubit. It has nothing to do with the second qubit.
Okay, and what I'm grappling with is that with this circuit, is it possible to end up with a set of vectors for the possibilities of X prime and Y prime that would be equivalent to applying a Hadamard gate to both of them? It's not, is it?
Is not really related. I don't.
I get what was confusing me at first, which
Yeah.
I still don't get it, but I know where to pursue it now, is that if X and Y are 0, you end up with an equal possibility that the X prime and Y prime are any one of the 4 possibilities. But that's only if X and Y inputs are both 0. And so
no. So here you're only applying one Hadamard gate. So you are only making this first one having an equal possibility of 0 and 1. However, this gets carried over when you're doing a C naught with your second qubit. That's what's making this an equal probability of 0, 0 and 1, 1. but there's no Hadamard that's being applied to
Okay.
the second one. Yeah, and this also reminds me of a tip here is when you are doing these programming, you usually, the initialization will make your qubits all be in the 0 state. When you're doing your algorithm, usually when you start is all 0. So if you want to make your qubit not being 0, you need to apply a gate to them to make them different. Just not really related to the states. I'm just talking about any programming that's convention.
Okay.
I think, yeah.
And the word Bell state only applies to situations where there is entanglement.
Can you repeat your question?
The term Bell state
Yeah.
only applies to situations where there are entanglement.
Bell states are the special states, the 4 states that have 2 qubits entangled.
Okay.
Yeah, right. Remember in the 3rd session, I think, when we talk about entanglement, we use Bell states as examples.
Okay. Thanks.
Yeah. Mm-hmm. Any other questions? Terrell, if not entangled, then when measure each separately, then I think he's trying to answer the question too. So he said a separate H gate to each, they would not be entangled, correct? Because you haven't really, Hadamard doesn't entangle, only Hadamard plus the C0 together can entangle them. So if not entangled, then when measure each separately, then the probability of 0 from X would be entirely independent of probability of getting 0 from Y. Exactly, yeah. They would be dependent once they are entangled. And that's what all those algorithms build upon. Any other questions here?
Yeah, Kitty, this is Aaron. How you doing?
Hi, Aaron. Good, how are you?
Doing good. I have a question about the class. Will we be able to get access to the Azure Quantum or get a certificate, maybe of completion for the class after we're done?
Not related to this class. This is really a grassroots effort, and I'm just teaching this for fun. The Azure Quantum Service is under private preview right now, and there is a form online that you can fill up to be on the private preview. It's a small it's gonna be a very big program, but we're slowly opening it up. So if you haven't heard about becoming an Azure Quantum customer, then just wait and wait for the public release.
Okay, thank you.
Mm-hmm, yeah. Yeah, so Aaron mentioned Azure Quantum. This is a service that allows you to access hardware through the cloud. Microsoft has Azure is our cloud, and makes perfect sense that you can program on your own computer and then submit to the cloud and then use the actual quantum computer to run your algorithms. So that's under private preview. We have some initial customers. Yeah, this class doesn't have certificates. Maybe you guys can help work on this, like maybe some kind of, but this is already free and all for you to learn for fun. And a lot of other quantum computing classes are really good, but you have to pay. So yeah, up to you. And I hope that this guides you to the point you to the resources that can really help you get up to speed. Yeah, okay, if there's no other, yeah, I could draw a certificate, that's right. If you like, I would give this out to people. We'll think about what's the mechanism? Because usually I will make people pass some exam in order to get it. So if I give you guys homework, would you do it?
Yes.
But then I have to grade them.
I'll be your TA and do the homework.
Yeah, we need to think about a way to, like, can you broadcast this to more people? If we hit certain number of attendees, we can give out certificates.
Yeah, I think maybe T-shirts, given your background, Kitty.
Well,
Maybe
T-shirts
full
is boring. Oh, actually, I have a new design. I have a earring that is a Schrodinger's cat. You can find it from my website. It's just made available this week. My name, kittyyoung.com, you'll find it. Yes, you can self-grade. Using the katas, it shows you the outcome. It tells you if you have done it correctly or not. You can actually also check the answer, but I would recommend you not to look at the answer before you finish. You write your own code. T-shirts are boring. Come on, guys. Okay.
Well, it
Thanks,
depends on the
everyone.
picture.
Yeah, see you next week.
My vote's still the happy face stickers. Thank you so much.
Yeah, thank you.
Thank you.
Yeah, thanks.
Thanks.